Now, before we move on, the differential equation is given on the bottom right of your screen, but to be honest, it looks quite clunky. So I'm going to make some simplifications. We're no longer going to write that it's a function of x. In fact, I'm going to imply that it's a function of x. And for the derivatives, I'm going to use primed notation for the 0th derivative, first derivative, and second derivative terms. So what I've just said there is expressed here, and that allows us to rewrite the time-independent Schrodinger equation in the following form. So both of these are the same, obviously. So we have minus h bar squared of 2m. We have psi double prime standing for the second derivative of psi with respect to x. We're implying x. There is no first derivative term, but just for clarity, I've put in the fact that its coefficient is 0. We have the 0th derivative, or just psi itself, multiplied by the potential energy, and then we have the same thing multiplied by the energy eigenvalue here. So I think this is a neater way of representing the differential equation. The next thing we're going to do is some algebraic manipulation. We're going to gather the 0th derivative terms psi. That's very straightforward. We're going to gather those, and we're also going to gather all of the constants together. And that's what I've written on the bottom of your screen. What we'll see in a moment is I'm going to gather all these constants in another constant, which I'm going to call k sub 1 to be squared. As a point to note, the reason I'm going to call it k sub 1 to be squared as opposed to just k sub 1 is that we're going to use the characteristic equation, which involves us taking the square root of whatever we call all of these constants put together. So if I put it in as k sub 1, I'd always be carrying around this square root k sub 1 at a later stage, and I'd rather not do that. So it's really for mathematical simplicity. So on the top of your screen, I've got the time-independent Schrodinger equation, as we discussed a moment ago, and we have all of our constants here. So what we're going to do is replace the constants here with k sub 1 to be squared. That is to say that plus k sub 1 to be squared is going to be plus 2m outside of e minus v over h bar to be squared. Now, to be honest, there's another way of defining the constants if we like. We could have minus 2m, and this time we would have to swap, of course, the e and the v. So we'd have minus 2m outside of v minus e over h bar to be squared. Now, although, of course, the constants are the same, it looks slightly different, and for that reason, I'm going to give it a different name. I'm going to call this one k sub 2 to be squared. So when we have 2m e minus v over h bar to be squared, I'm going to call it k sub 1 to be squared. And when we have minus 2m outside of v minus e over h bar to be squared, I'm going to call it k sub 2 to be squared. And to be honest, this is very important because by defining the constants in this way is going to give us different looking solutions to the time-independent Schrodinger equation. And that's very important because sometimes different looking solutions or different ways of expressing the solutions allow us to look at the science or the physics in a simpler manner. So what I have in front of you is basically a summary of what we've done. We had the time-independent Schrodinger equation, which is given on the top center of your screen. We defined the constants k sub 1 to be squared and k sub 2 to be squared. And if you plug those into the time-independent Schrodinger equation, you're going to get two different looking time-independent Schrodinger equations. Note, that it's plus k sub 1 to be squared times psi on the left, and it's minus k sub 2 to be squared times psi on the right. And this plus and this minus is going to be crucial because that's what's actually going to change the way the solutions will look. What we'll see later is that this is going to have solutions which is a linear combination of cosines and sines. In other words, it's going to be a complex exponential solution. And this one is simply going to have real exponential solutions. However, the information which these solutions hold, or the science behind them, is going to be the same. They just will look slightly different.